Here we go with energy. So we have the moving energy, 1/2 mv squared, mass times velocity squared, and potential. That's how much is stored. So you think of a battery, that would be stored energy ready to be released. The equation we're going to use is mass times gravity times height, because we're mainly in year one talking about if you have something at a certain height and you drop it, how much energy is going to be created from that. As always, matter cannot be created nor destroyed. Energy cannot be created nor destroyed. So the conservation of energy is exactly the same as the conservation of matter. We are just going to replace the word matter with energy. So there's a lot of theorems that work on that one. But you can't just assume that kinetic energy becomes 100% potential energy. Do the math, work through the situation. The energy before a collision is going to equal the energy after a collision. The energy at the start is going to equal the energy at the end. So you have to include both kinetic and potential on both sides. Now, the one that they do touch on a little bit for potential energy is a spring. I want you to think of a rubber band, since you might not have done much things with a spring. Okay, the rubber band naturally is a certain size, and then you can stretch it. Okay, if this guy is 1 centimeter and this stretch is registered at 10 centimeters, then we have 9 centimeters is the change in the distance for the stretch. And that stretch is what is storing that energy. We now have all that energy in the stretch. So if we let go of one side, it's going to fling to another one. So you are able to build a relationship of the force and the stretch. Okay, and so that's the stretch in meters. That's not the mass. Those are the units of meters. And the force, as always, is in newtons. And so it has a force equals KD or force equals KX as opposed to MGH. The K is very specific for that string or that spring or the rubber band. It is that constant that is going to be worked with it. So just be aware of those, but you typically don't get many problems on springs in year one. It's more like these ones with the hills. What is the potential energy and kinetic energy? The top and bottom of a hill. Is a drawing going to help you? Yes. We have the top of the hill. We need to know the potential energy and the kinetic energy. At the bottom of the hill, we need to know the potential energy and the kinetic energy. These guys are the final energies. These guys are the initials. You could also see it potential energy 1, kinetic energy 1, and the final being listed as a 2. Okay. The hill is 100 meters tall. There's a 14-pound bowling ball. Do we use pounds? No, we don't use pounds. So make sure you convert that to kilograms is what we use mainly in physics. Okay. At the top of the hill, it's at rest. The velocity at the initial is 0 meters per second. So when we look at our formulas, that means our kinetic energy is 0. It's not moving. But our potential energy is mass times gravity times height. Mass is this guy converted to kilograms times gravity, either 10 or 9.8. Again, read the problem really carefully. And your height would be how much it's able to go down. So it's able to go down 100 meters. That's kind of just like almost an abstract quantity because we don't know if the mountain's going to be taller or what else is going on. So it kind of just throws that at you. And at the bottom, it's traveling 44.27 meters per second. Meters per second is a velocity. So 1/2 times that mass times 44.27 squared. The potential energy at the bottom, again, arbitrary, but for this reaction, it's at the bottom. We don't know if there's another hill, but when we're comparing these guys, it has no height left. So the potential energy is 0. I just want to make sure you're clear. Draw the picture, use your math based on your picture. Okay. And there is that conversion 6.35 for your math. So you can plug that in at the top and the bottom to get your answers. Okay, and there it is, just written out a little bit prettier. Usain Bolt is 207 pounds. Guess what? We got to change that to kilograms. Took 9.58 seconds. So this time I'm giving a time to run 100 meters. That is our distance. Okay, that is not a hill though. So pay attention to what things we're talking about. He is on a track. So kinetic and potential energy are going to look a little bit different on the track, right? So what are our formulas? Kinetic energy, 1/2 mv squared. Potential energy, mgh. We have no height. So anything times 0 is 0. So he's running on the track. He has no potential energy. Even when he's at the starting gate, technically has no potential energy, even though his body has some stored potential energy. But in terms of the macro view for this, he would have 0 potential energy. 1/2, make sure you convert that 207 pounds to kilograms. Velocity, what do I need to find velocity? I'm going to go back and look at my equations. And the average velocity is the change in distance over the change in time. So in this case, I can use 100 divided by 9.58 to get my velocity and plug it in. Not always. So make sure you read the problem carefully and see if you need another velocity final equals velocity initial. But they just gave us the averages. They gave us the total distance and the total time. So I'm comfortable just dividing those two for my velocity to solve my problem there. So just make sure you do your conversions when you do that. And there you go if you want to check your work. And hopefully I don't have any errors in my work. I do sometimes. If I do, always just let me know. Compare the potential energy of 2 bowling balls at the top of 2 different ramps. 2 different ramps. Okay, bowling ball 2. So the first one, I'm just going to say my ramp is height h. The bowling ball's up here, and he is mass m. So his potential energy is mass times gravity times height. My second one, bowling ball 2, has 3 times the mass. So 3m and half the height of the hill, h over 2 for his hill. So his potential energy is 3 times the mass, 3m. Gravity's still the same, and his height is h over 2. So when I look at that, what do I have left? 1.5 mgh. So the second bowling ball is going to be 1.5 times the first one. If these algebra ones give you trouble, in the initial settings, what you do over here, make up numbers. Give it a mass of 1, give it a height of 5, and calculate your potential energy. And then over here, instead of h over 2, put in 2.5 into the equation. Instead of 1 kilogram, we know it's 3 times, so put 3 kilograms. And then find the answer this way. 3 times g times 2.5, and then compare your results. When you compare your results, see which one is bigger and by how much, and you'll come up with 1.5 times again. But don't freak out when you see those algebra ones if you're not strong in algebra. Just put in fake numbers to get your answer. A braking system abruptly brings a 333 kilogram car, including the rider and all the stuff in the car. So you just use that as the total mass, traveling at 30 meters per second to 10% of its speed. So at the start, that's my velocity initial. Meters per second is a velocity. So my starting velocity is 30 to 10% of its speed. So what's 10% of 30? 3 meters per second. That would be its velocity final over a distance of 8.9. That is not a height. Okay, that is a car just driving on the road. So that's a distance. Determine the magnitude of the braking force in newtons. Okay, start with a problem, because when you do the final and do higher level physics problems, you're not going to know where they're pulling it from. So every time, draw a picture. Okay. We don't have a force applied. We just have the braking system. Remember, the brakes are the friction. Okay. What else do we know? We know the force of normal is equal to mass times gravity, because the force of normal is going to equal the force applied. Okay. And then we know there is some sort of acceleration. Why? Because there's a change in velocity. So when we sum the forces in the x, we're going to have the force of friction equals mass times acceleration. That force of friction and mass times acceleration are both our net force or our sum of our forces in the x direction, which is basically what we're looking for, the braking force. Okay. So now when I look at it, do I have a force of friction? No. What's another way to do force of friction? Mu times the force of gravity, or mu mg equals ma. Then I can cancel off my m's. Okay, so my acceleration is mu times g, and then I can figure out my force of friction. What didn't they give me? Okay, now they didn't tell me if I'm going to use 9.8 or 10, but there's a bigger thing they didn't give me. They didn't give me the coefficient of friction. So while I was hoping this was a module 3 question, it's not. I have to go further. What other information do I have out there? Oh, module 1. What things do I have from module 1? Look at this. I have a mass, I have a VI, I have a VF, and I have AD. So I have a lot of information right here. Is there any other equations that use that? Let's look. Do I have a velocity final? Yes. Do we have a velocity initial? Yes. Do we have a time? No. Do we have an acceleration? No. I know it's mu g, but I don't know mu, so I can keep that in the back of my brain in case I need it later. Do I have a velocity final? Yes. Do I have a velocity initial? Yes. Do I have an acceleration? No. Do I have a distance? Ooh, this might be a good one. Let me go on, but that's looking like that might be a keeper because I can find the acceleration. And once I have the acceleration, I already know the mass. So then I could find my force of friction or my sum of the forces in the x direction. The sum of the forces is mass times acceleration. That just confirms what I just thought. If I get that acceleration, I already have the mass, and then I can find my magnitude there. So velocity final squared equals velocity initial squared plus 2AD. 3 squared equals 30 squared plus 2A times 8.9. So I'm going to solve that for A. Okay, and then I'm going to multiply that times the mass to find my force. There's your answer. If you're getting stuck in the algebra, yes, sign up for a one-on-one appointment. I don't have time in these short little overviews to go over each part. And you can always come to the live sessions as well. Have a great day.